In this video, we're going to look at how we can use a titration curve to determine the Ka for an unknown acid. So let's draw that curve in and do the best of my abilities. It's kind of ugly looking, but the key points are on there: the starting point, the halfway point, and the equivalence point. Now we're going to use each of these points 3 times, once for each one, to find the Ka. Hopefully our values should be similar to each other, right? Because it's the same acid. It's one titration curve. And I should mention that we're going to use a 0.1 molar HA acid, and let's just say we have 100 milliliters of it. Since the 0.1 molar and the 0.1 molar match up, the M1V1 equals M2 calculation is going to be pretty simple. When their volumes are equal, that's when we have reached our 1 equivalence. When our volume of NaOH is half of 100 milliliters, that's when we are at our half equivalence. And when we have added 0 milliliters of NaOH, that is when we are at our starting point. So at the starting point, the HA is going to either react with NaOH or water. And since there is no NaOH, then we can only react with water. And it's going to undergo its standard equilibrium dissociation. We start with 0.1 molar. It's going to change by some amount. Call that X. Nothing initially dissociates until it starts changing, right? This X is directly proportional to this X. And so at equilibrium, we have these values, and we can write a Ka expression. Products over reactants, X squared over 0.1 minus X. And we're trying to find Ka, right? So the only thing we need to find Ka is if we can know what the X value is. We can see that this X value corresponds directly to H3O+. And what do we know H3O+ corresponds to? That corresponds to pH, right? Because the negative log of your H+ equals pH. Or if we solve for the H+, H+ equals 10 to the negative pH. In this case, that pH right here looks to be about 2.8 or 2.9. So let's just call it 2.85. Plug that in. We'll get some H value. Plug that in for X, and we'll get some Ka value. After you chug all this stuff in, the Ka value that you're going to find is 2.06 times 10 to the negative fifth. This is the Ka generated from looking at the starting point. Alright, now let's do it for our halfway point. I'm going to recopy the graph down here so we can see it better. What's true at our halfway point? At our halfway point, let's say if we had 10 acid, the halfway point would say that we have 5 OH. And what this means is that this will generate 5 A- and 5 HA, because these guys are going to react completely. HA plus OH minus goes to A- plus H2O, 0.1 molar times 100 milliliters is 10 millimoles. 0.1 times 0.5 equivalences, or 50 milliliters, is going to be 5 millimoles. Limiting reagent, right? So minus 5, minus 5. We're going to generate plus 5 over here, because this is minus 5 minus x plus x. So what we're left over with is 5HA and 5A minus. This is really nice, because from the Henderson-Hasselbalch equation, we know that pH equals pKa plus log A minus over HA. Since A minus in this case equals HA, we're taking the log of 1, and the log of 1 pretty much equals 0. So at this point, pH equals pKa. pH looks to be about 4.7, I think. 4.7. So then 4.7 equals the negative log of your Ka. Hence Ka is going to equal 10 to the negative 4.7. And this equals, after you plug it in, 1.99 times 10 to the negative fifth. And if you remember our previous value was 2.06 times 10 to the negative fifth, which came from here. And these are pretty close to each other, so we are on the right track. Alright, let's get to our third point. I'm going to copy the graph over one last time. At our third point, we have reached the equivalence point, which means that when we start out with HA plus OH minus going to H2O and A minus, that our starting amounts are going to be equal. They're both going to be 10 millimoles. Zero products. And when we do our stoichiometry, we know that these are both going to react completely, right? So the final amounts for our reactants are going to be 0. As always, water doesn't matter. This is minus x, plus x. So what we have at equilibrium is purely A minus, and it's going to be 10 millimoles. And since at this point right here we've added 100 milliliters of NaOH, our final volume is going to be 200 milliliters, meaning our A minus concentration is going to be 0.05 molar. Just a quick reminder, molarity equals moles per liter. So molarity can equal millimoles per milliliter. Millis will cancel out. We're almost out of time in this video, so I'm not going to be able to take us all the way to the home stretch. But here's the basic idea of what's going to happen, and you can do the rest at home. The A minus is going to go back into equilibrium with water. This is going to generate OH minus, and this is going to undergo a equilibrium reaction. The Ka for it, psych, right, because it's a base now. The Kb of it is going to equal that x squared minus your concentration minus x. From your Kb, you can find your Ka, right? So all we have to do is find Kb. We know that x represents OH minus concentration, and from the pH, we can find OH minus concentration. So best of luck. Sorry for the rushed finish, but I hope you enjoy this video, and I will see you later.